Hi everyone, welcome to subscriber video number 4. This video was requested by Orange Drawer about something mathsy. I've decided that we're going to give a bird's eye, like speed train, like bullet train approach look at optimization. Now, why might we want to do this? Let's suppose that we've done some experiment and we've measured two quantities that we believe are related. So here on the graph we have the x or horizontal axis representing one quantity and the y or vertical axis representing another. And these dots match each x point with its corresponding y point from all of the observations that we've made. And we're trying to find a relationship between the two quantities so that if we can only measure x, whatever that is, for someone, then we can get a reasonably good estimate for whatever this y quantity is. Fairly standard examples are weight and height. It's easy to measure someone's weight, it's harder to measure their height. You might think it's the other way around, maybe it is. The point is, it's not particularly important, but you just measure one and you get an estimate of the other. Now, there are many different relationships that these could be. Here is some examples. It could be this red line. It's probably not because it's going in the complete opposite direction and it's not even vaguely close to our data points. This magenta type line, at least it's increasing as we go from left to right, like our data points are, but it doesn't feel right. This blue line, it's increasing about the right amount, but it's like it's shifted a little bit. What we really want is something like this green line that kind of goes through our data and goes up at the same rate. And how do we actually work out what that is? We're not going to work with this data set. We're going to work with a simpler one, but just some definitions first. We're going to suppose we're given n data points, and then we're going to label them xi and yi. And we're restricting ourselves to look at a straight line relationship. So on the previous slide, it's these types of relationships here. We're not looking for if there's a curve or anything more complex, just a straight line relationship. What that means is we need to find values m and c that relate the y value to the x value. This is a fairly standard expression for writing a linear equation. And what we're really trying to do is minimize the error between that estimated relationship, so this guy, and the data points that we have. So this red line, we can see out here, we're going to have lots of error. We're going to have lots of error over here. Less error in the middle. The blue line, we're going to have fairly consistent error the whole way along. The green line is going to be much smaller than all of the others because it's closer, much closer to them. Now, the type of error measure that you use can influence that relationship, as well as a bunch of other things we're not really going to touch on. Now, our simple example. We've only got 3 points. Points 1, 1, 2, 2, and 3, 2. You should be able to convince yourself fairly quickly that we can't draw a straight line that goes through all 3 of these points. If it goes through 1, 1 and 3, 2, it's going to miss that point 2, 2. If it goes through 1, 1 and 2, 2, it's going to miss this point 3, 2. And if it goes through 2, 2 and 3, 2, it's going to miss 1, 1. So we're going to have to estimate them somehow. Now, how can we do that? Let's suppose we're just going to guess a line. We're going to guess this red dotted line. Let's suppose that that's the line that we're looking for. Maybe it is, maybe it's not. It seems like it might be okay because at least it's between, it's going between our data points. It's not like down here somewhere or way up the top. It could be okay, but we're just going to guess one. It doesn't even matter if it's right or not at this point. But how are we going to measure the error to that line? Well, there are 2 possible ways. The first is measuring the vertical error from our data point to the line we're estimating. This is particularly good because it's fairly simple to measure. We know our y data point, in this case for our sample is 2, and we can substitute x equals 2 into this line once we know that m and c value to work out this point, and then we can take the difference. The downside of using this approach is that we're assuming that our x value is perfectly correct. So we've been able to measure it exactly. And that's not always the case. In the case of our height and weight example earlier, you don't really measure either of them precisely. There's a small margin of error in them. In that case, instead of measuring the error vertically, you can measure it perpendicular to the line. So this allows some error in both the x value and the y value, but it's going to be a little bit harder to measure because instead of now working out this point here, we need to work out this point over here. But we need to work out both the x and the y value, which we can do, it's just a little bit harder. And then we need to work out the distance of a diagonal line. Again, it's not impossible, it's just a little bit harder. But you get a little bit extra flexibility in your optimization approach. Now, what we're ultimately going to do is use the first one, simply for simplicity. Now, we can consider a sample of lines. Here we've just picked one. I've shifted up from our previous examples slightly a little bit. So here you can see it goes through all of the points, like it goes between the points, sorry. It doesn't go through any of them. We're going to guess a line that just happens to go through this point 2, 2. And it's this line, y equals 0.5x plus 1. That's when we have m equals a half, that's the number near the x, and c equals 1, that plus bit on the end. And we're going to work out the error for each point. Now at the point 1, 1, so this guy over here on the left, we know the y coordinate, it's 1, and this value up here, we're going to substitute into our formula. So we have the 0.5, we're multiplying it by the x value, which is 1, and then adding 1. If you plot all of that into your computer, or calculator, you get negative 0.5. That kind of makes sense, because it's below the line. Next, at the point 2, 2, we substitute in again. We have our y coordinate, I haven't labeled each term this time, of 2, minus 0.5, that's the m, times 2, that's the x value, plus 1. Your calculator this time will give you 0. And we can see from the graph that it does indeed go directly through that point. So a 0 error makes sense. And also at the point 3, 2, we can do the same thing. Our y value of 2 minus the m is 0.5 times 3, our x value plus 1, we get negative 0.5 again. So now we've got these 3 different errors for all 3 points. How do we combine them in some way? Well, there are, again, many ways you can do this. I'm just going to list out 2. The first one, we can just sum the absolute error from each data point. So the absolute error is just the number, and you ignore the sign. So this first one is 0.5, the next one will be 0, and the last one would be 0.5. That's an absolute error. For the square of the error, we square each of these before we add them up. So if we're looking at the absolute error, I've labeled it E. We have the absolute value of negative 0.5, it's the error from the first point, plus the absolute value of 0, the error from the second point, plus the absolute value of negative 0.5 again, this is from the third point. You add all those up and you get an error of 1. Now that approach is okay, but using this type of error metric, it's a little bit harder to reason about more general cases. And that's why the second error measure comes up, where we sum the squares of the error. So we take negative 0.5 from 1, 1, and we square it. And then we add on the 0 error from the second term, and we square it. And then we add on the negative 0.5 term from the third, and square it. When we add them all up, we get 0.5. Now, even though this is smaller than the number we saw earlier, with a different way of measuring error, it doesn't necessarily mean it's better. We're still looking at the same line. So we have to be consistent when we're using error metrics, but we're going to stick with squaring the error because it gives you, how would you describe it? It's easier to reason about the error fitting process. Now, how would we go about actually working out what M and C are without picking values and just guessing all of them? Well, let's just assume that the line is mx plus c, like we have done. Now, we know the error, like we've worked out what that error is so far. At the ith data point, so xi and yi, the error is the y value minus m times the x value plus the constant. So we can do that. That's what we did back here. The y value minus m times the x value plus the constant. So we've done that. We're just being a little bit more general now. And then we need to square all those errors and add them up. When you do that, we get this here. So this is the first term, a 1, 1. So y minus m times 1 plus c, all squared. Plus, this is the second term, 2, 2. 2 minus m times 2 plus c, all squared. This is our third point, 3, 2. So 2 minus m times 3 plus c, all squared. We can expand those brackets and simplify, and you get this conic expression here. There is a formula to work out what the minimum value of that is. We're not going to go through all of that rigmarole. If you want to find the minimum of that, I'd encourage you to do so. I'm just going to tell you that it happens with m equals 1/2 and c equals 2/3. So if we choose m as 1/2 and c equals 2/3, that's the line that minimizes the error. So a relationship right back here at the start that we're looking for between these points is y equals 1/2 of x plus 2/3. And on this next slide, I've got it drawn here. So you can see it's almost exactly the same as that red dotted line that we had earlier. I've just shifted it slightly a little bit. And that process that we've just done for 3 points generalizes to any number of points. So if we have n data points, the process for minimizing the square of the error is exactly the same. So we work out the error from each data point, the y minus m times x plus c, we square it, and then this sigma means sum them all up, starting from I equals 1, going up to n. Now you can actually work out what the minimum value of this is. I've said here with calculus. There's a whole bunch of ways you can do it. I said with calculus because I use calculus to solve it, because it was easier for me. So we can firstly work out the m value. This is just a formula. It's a complicated looking formula, yes, but we can work out each of these. N is just the number of data points. The x's and y's we know. We can multiply them together and add them up. We can add up the y's. We can add up the x's. We can square them and add them up, and we'll get some number for m. It doesn't matter what it is, but we'll get some number. And then once we know what m is, we can use the second equation to work out what c is by substituting in the m. So that process, if you did this for our example earlier, this guy, you get the exact same line. It's no different. It's just slightly more general way of looking at the problem. Now, we've been extremely limited in what we've looked at here. We've only looked at a very small number of a very small subset of optimization problems. So things we haven't looked at is if there are more complex levels, so more variables. What if instead of measuring height and weight, you measure height, weight, and their waist diameter, and look for a relationship between their height with the waist and weight. There are many other human measurements that you could take to relate them. We haven't even looked at that. You could have more complex relationships. So we only looked at linear, so a straight line. It could be quadratic, or a spline, or anything else. We haven't even touched on them. We didn't even talk about them as an option. We just nope, we're not doing it. Different error metrics. I raised 2. The absolute vertical error, so that was our option 1, that we pretty much just wrote off. Oh no, that's the one we used, wasn't it? Our vertical error. Or the perpendicular error. We also didn't use that. Again, something else that we could use. And different error metrics will give slightly different lines. There are also constraints that we could apply. Suppose we need it to be particularly smooth, like it can't kink too much. If we were trying to work out the equation of where a hose should go, or tubing that can't have a sharp kink, that's where smoothness constraints would come in. But there are many others that you could apply that depend on the particular problem you're looking at. And we've not even touched them. So all of those still fall under this concept of optimization problems. And they're all there for you to look at. Hopefully this has been interesting for you to have a sky high skim past of what optimization problems could be. If you have any questions, feel free to ask in the chat, in the comment section down below, or ask in the Discord. Thanks everyone. I'll see you in the next video. Bye for now.